Welcome to the deep dive. Today, we are taking, well, the ultimate plunge. We're going into the most complex, maybe the least understood frontier of the human body, the brain.
It really is.
We've got this stack of sources that really challenge centuries of medical belief. And it's all guided by this unique perspective of a practicing brain surgeon, someone who's seen the raw resilience of consciousness firsthand.
Yeah, and for such a long time, the brain was kind of the medical equivalent of a dead end, wasn't it? The established thinking, the doctrine really, was that once nerve cells in the brain or the spinal cord were damaged, that was it.
Right. No going back.
Exactly. Unlike skin or bone, repair, regeneration, impossible. So this deep dive, it's our mission to unpack how cutting-edge neuroscience is finally starting to overthrow that assumption, moving us from just treating decline to, well, maybe achieving actual repair.
And to really get that shift, I think we have to start right there, in the operating room. Our sources describe this kind of overwhelming reality of holding the organ of consciousness. But just practically, how does a surgeon even get in there? What's the technical process? Opening the skull, navigating that incredibly delicate pink tissue.
It's an amazing mix, really. High-tech tools on one hand, extreme delicacy on the other. To get to the target area, a tumor, maybe a lesion, the surgeon uses electric drills and specialized saws to essentially carve out a piece of the skull.
Like making a window.
Pretty much. This piece, they take it out, set it aside carefully, and put it back later. The source calls it a door flap. The whole point is precise access, usually guided by imaging they did beforehand.
Okay, so once that door is open, the stakes are just unimaginable. The surgeon isn't just dealing with, tissue. They're navigating memory, motor function, personality itself.
Absolutely.
So when you have to take out a tumor, how do they handle that risk? The risk of cutting the connections, the sort of paths that link crucial functions?
That is the absolute core difficulty of neurosurgery.
Yeah.
You might successfully remove the tumor, brilliant, but in doing so, you might sever the connection between, say, function A and function B.
And the person might not even know.
That's the really profound thing our sources highlight, this potential for unknowable loss.
Yeah.
Because the brain itself is what processes loss, right? So patients may live seemingly normal lives, but they lack specific memories or aspects of their personality, and you don't know what you don't know.
Wow.
They don't know they're missing it. It's often the family, the people close to them, who notice a shift first. Maybe the patient becomes angrier or less tolerant, maybe quieter after the surgery or an injury.
That paints such a powerful picture of how fragile the brain is. But then the sources also give us this shocking proof of its resilience, too. Can you share that anecdote?
Yeah.
About the worm cyst. It sounds like one of the strangest things ever found inside a skull.
Oh, it's truly bizarre. Yeah. The source describes removing the largest recorded collection of worm cysts from a patient's brain. We're talking a palmful of these cysts.
Palmful.
A palmful. They had apparently eaten right through the skull, yet despite this, catastrophic infection, the patient not only survived, but actually recovered.
Incredible.
It just highlights that while the brain is delicate, incredibly so, it also has this innate, almost shocking ability to bounce back, to heal.
And that resilience, that's exactly what the old medical doctrine just ignored, right?
Completely.
So let's pivot now to this era of regeneration. Why did medicine insist for so long, nope, nerve cells can't be repaired? And how did a surgeon, move past that scientific, almost heresy?
Well, the belief system was rigid, partly because, nerve cells don't regenerate in the same simple way that skin or bone does. That's true. But the surgeon in our sources, they credit an early anatomy professor with planting the seed, this idea of always questioning the written word.
Don't just accept it.
Exactly. When the traditional tools, drugs, surgery couldn't fix chronic neurological damage, the only logical next step was to look for the body's own repair mechanisms. And that leads you straight to cellular therapy, stem cells.
Okay, stem cells. So not a drug, not surgery, a biological healer. How does that actually work inside the brain? How does it repair damage?
Think of them as the body's internal construction crew. They kind of repair damage in three main ways. First, they're pluripotent. That means they can multiply and, crucially, transform into whatever cell type is needed right there, a new nerve cell, maybe a muscle cell, whatever is damaged.
Okay.
Second, they release these really important growth factors, like signaling molecules that tell the area, okay, time to heal. And third, they encourage angiogenesis. That's the growth of fresh blood supply. Absolutely vital for bringing nutrients in and clearing waste out from the damaged spot.
And the surgeon prefers autologous cells taken from the patient's own body, likens them to fresh orange juice. What makes those better than, say, stored cells from umbilical cords?
Right. Autologous cells, usually they get them from bone marrow or fat. The big advantage is the body accepts them immediately, no rejection issues. And they're fresh. No preservatives, no cryo-freezing like you need for stored allogenic cells from someone else.
And that freshness is key for how they deliver them.
Precisely. That freshness allows for this really unique and highly effective delivery method, injecting them directly into the cerebral spinal fluid, the CSF.
The CSF. That's basically the brain's internal highway, isn't it? It flows all around the brain and spinal cord.
That's a perfect way to put it. It bathes and circulates everywhere.
So if you inject these fresh stem cells into the spinal column, into that highway, how do they know where to get off? How do they find the specific damaged bits of the brain that need fixing?
It's an amazing mechanism called homing in. The damaged areas of the brain, they're metabolically distressed. They're essentially hungry. They give off specific chemical signals like flares. The stem cells traveling in the CSF, they automatically follow these signals. They're drawn right to the non-functioning hungry areas that need repair. And the healthy parts, they're full. They don't send out the signals, so the stem cells just pass them by. It's incredibly targeted.
That's ingenious. Okay, let's shift to where this tech seems to be making some of the most startling breakthroughs, specifically neurodevelopmental disorders. Our sources mentioned these, frankly, alarming CDC statistics on autism spectrum disorder, ASD. What are those figures again?
Yeah, the stats are undeniably worrying. The incidence of autism, according to the CDC figures cited, was about 1 in 160 children just 10 years ago.
Okay.
Today, that number is reported as 1 in 36.
1 in 36. That's a staggering increase.
It is. And that kind of exponential rise, it really demands we look hard at environmental factors, diet, lifestyle, whatever the core biological cause might be, something's changing rapidly.
So using PET CT scans on thousands of kids with ASD, the research uncovered this pattern, something that completely reframes how we should maybe view this disorder. What did they find about the lower brain versus the higher brain activity?
This is the key neuroscientific insight, really. It's not a uniform problem across the whole brain. What they found was the lower brain, the more primal, animalistic, instinctual part, responsible for basic functions.
Yeah.
That area is often hypometabolic, meaning it's underactive, it's damaged, it's not firing properly. But conversely, the higher brain, the area for logic, creativity, math, abstract thought, that is often hyperactive.
Working more than in neurotypical kids.
Frequently, yes.
Yeah.
Working much harder.
So the incredible intellectual potential might actually be there. But this damaged, underactive lower brain is like a broken foundation. It's stopping that potential from coming out.
That is the perfect analogy the source uses. The underactive lower brain is the fracture, and it's preventing the great athlete, that hyperactive higher brain, from actually performing, from showing what it can do.
Wow.
So, by fixing that fracture, using the stem cell therapy to repair the lower brain's metabolic function, suddenly these innate abilities, already present in the higher cortex, they get unlocked.
Which leads to this phenomenon of savant abilities just emerging. We're talking kids suddenly showing genius-level skills after treatment.
Yes, exactly. The source gives these incredible examples. The 7-year-old math prodigy who could seemingly, read minds for numbers, just knew the answer instantly.
Wow.
Or the boy who went from being nonverbal to topping his class, showing these amazing savant-like math abilities. Or another child who, after treatment, could recite the entire Holy Quran by heart, despite having basically no speech before therapy.
That's mind-blowing.
It really is. These unique, often unimaginable skills were apparently already there inside the patient's higher brain, just blocked by the damage in the lower structure.
It sounds like a medical miracle,
Yeah,
honestly. Yet therapy like this, it hasn't exactly swept through Western medicine, has it?
No, it hasn't.
We have to touch on the resistance. The source uses this phrase, an existential threat. Is that really about the science, or is it more a commentary on cost, on disrupting the status quo?
It's a very powerful claim, and it seems to point squarely at economic inertia. The source reports a multinational executive actually described this kind of therapy as an existential threat.
To whom?
Well, not just to big pharma, apparently, but to the entire rehabilitation economy. Think about it, all the long-term, expensive industries built around managing chronic conditions.
Right, like chronic care facilities, certain types of therapy, maybe lifelong medications for some things.
Exactly. Speech therapy, maybe lifelong insulin dependence in some models.
Yeah.
All these things are built around managing conditions that stem cells potentially, threaten to eliminate or significantly reverse. So disrupting that vast economic structure, well, it naturally creates institutional resistance, regardless of the clinical success stories.
That definitely provides some critical context for why adoption might be slow. Okay, let's move inward a bit now, from clinical repair to sort of self-management. The source talks about the hot brain versus the cold brain. That seems like a really powerful model for understanding our everyday struggles. How do those two systems clash?
Yeah, it's a useful way to think about it. The hot brain is our primitive core, right? Impulsive, animalistic.
Yeah.
It wants instant gratification food, anger release, addictive behavior, whatever.
Okay.
Now,
Good.
the cold brain, that's the higher cerebral cortex, logic, planning, thinking about long-term consequences. And a lot of our unhappiness day to day comes from that constant internal battle. The hot brain screaming, I want it now. And the cold brain saying, hang on, what about tomorrow?
So the 6 a.m. alarm versus the snooze button, that's the war right there in my head every morning.
It's a perfect, simple example, exactly.
So how do we neurologically hack this conflict? Without necessarily forcing ourselves into hours of meditation, which is hard for many people. What's the discipline hack the source offers?
The most powerful solution offered is cultivating a definite chief aim in life, a really profound sense of purpose.
Purpose.
Yes. When the goal set by your higher brain, your cold brain, is important enough, truly meaningful to you, that purpose automatically gives you the motivation needed to override the hot brain's demands for instant gratification.
I see.
The source quotes this great definition of discipline, choosing between what you want now and what you want the most. When you have that clear aim, that want the most, it aligns your whole nervous system towards it. The cold brain wins more easily.
That focus on the long term, it ties straight into anti-aging concepts too. Our sources talk about measuring biological age using telomere length. How reliable is that? And what does it tell us about how long we're sort of programmed to live?
Telomere length, basically the protective caps on the ends of our chromosomes, it's considered a highly reliable metric of cellular aging. Generally, the longer your telomeres, the younger your biological age.
Right.
And genetics suggests our maximum potential lifespan programmed in is somewhere around 120 years. The surgeon in the source material actually tested this personally, found his cellular age was significantly higher than his actual chronological age.
Oh, wow. So what did he do?
By incorporating some non-invasive therapies, specifically ozone therapy and hyperbaric oxygen, he was able to scientifically track and verify a significant reduction in his biological age. From, I think the numbers were 85 down to 60 at the cellular level.
That's amazing. But it also suggests that while biohacking can use fancy tech, the real foundation for longevity might still be these 5 simple, basically free pillars.
Absolutely. The source emphasizes that something like 80% of life's problems health-wise can probably be prevented just by sticking to these fundamental requirements, the things that fuel your cells properly.
Right.
Sufficient oxygen, deep breathing, pranayama is the term used. Water aiming for maybe 2-3 liters a day. Natural food, 3 natural unprocessed meals daily. Circulation, getting about 30 minutes of exercise to move your lymph, your blood. And critically adequate sleep, 7 to 8 hours.
The basics.
The absolute basics. They're the body's own natural healing systems. We just have to enable them.
Okay, finally, let's try and connect some of this cutting-edge science back to maybe older wisdom. The source material draws this strong parallel between modern physics, seeing all matter as just protons and electrons whizzing around, and ancient spiritual ideas about oneness, about intention.
Yeah, it's this fascinating convergence, isn't it? Physics today breaks down everything, whether it's you, me, or this table, to the same fundamental rotating bundles of energy, protons, electrons.
Right.
And spirituality, for millennia, has offered this accessible framework for understanding that fundamental unity, that we're all connected at some base level. And the power of intention, which the source emphasizes, really willing a goal, not just wishing for it, that aligns the brain's 100 million neurons towards a single point, it dramatically increases the probability of achieving that purpose. It's focus amplified.
That alignment, it is powerful. Which brings us, I suppose, to the ethical boundary, the one the surgeon strictly maintains. If stem cell therapy can repair a damaged brain, unlock latent genius in someone with ASD, what happens if a parent, a normal parent, wants to enhance their already healthy child? just to make sure they're top of the class.
And the surgeon says no, absolutely refuses such request, views it as a profound misuse of the technology. The ethical line for them is clearly drawn at healing and restoration, not vanity, not competitive enhancement, because when you consider the kind of leaps in ability they saw in the ASD children, that instant numerical genius, the massive memory, we're using that same power just to boost a competitive trait in a normally functioning brain. Well, you could fundamentally alter human evolution in some really unpredictable, potentially dangerous ways.
The fear being that playing God might create something worse than just a really smart kid. What specific kind of enhancement worries the surgeon? What could give rise to these supervillains the source mentions?
It seems to be about enhancing ambition and cognitive horsepower without necessarily enhancing the corresponding moral structure. Imagine taking someone already highly competitive, maybe morally flexible, and giving them this massive technological boost, superior logic, memory, focus.
It would create a very effective problem.
Exactly. You create a significant societal risk. The argument is the technology has to remain a tool for mitigating damage, for healing, not for engineering some new, potentially dangerous elite class based on enhanced brains.
A really sobering thought to end on as this science just keeps accelerating. When we get the keys to unlock the full potential of the human mind, maybe the most critical question isn't just what can we do, but what should we do? And who gets to decide? You now have the material, synthesize these insights.